Hey friends, welcome to the YouTube channel All About Electronics. So in the previous video, we learned about what is latch and flip-flop and what is the difference between two of them. So in this video, we will learn about the SR latch. So we will see the basic design and the working of this latch, and then after, we will also see the design of the gated SR latch. So as I said in the previous video, the latch and flip-flop are made up of the logic gates. Now we know that the logic gate itself does not have any memory and they cannot store the binary information, right? But using the feedback from the output to input side, they can be used for storing the one bit of information. So let's say we have two NOT gates and the output of one NOT gate is connected to the other NOT gate. And let's say on the input side we have a two-way switch. So on one side it is connected to the input, while on the second side it is connected to the output of the second NOT gate. Now let's say initially this switch is connected to the input side. So initially the 0 will appear at the input of the first NOT gate. So this NOT gate will invert that input. That means its output will be equal to 1, and that will be given to the second NOT gate. So if we see the output of the second NOT gate, then that will be equal to 0, and the same will also appear over here. Now instantly, let's say this switch is connected to the second side, or in other words, now it is connected to the output of the second NOT gate. So now the same 0 will also appear at the input of the first NOT gate. So if we see the output of the second NOT gate, then that will be equal to 0. That means in this condition, the output of the second NOT gate will remain 0. Or in other words, the circuit is storing the logic 0, right? Similarly, we can also store logic 1. So let's say initially the switch is connected to the input side, and now this input is equal to logic 1. So the same logic 1 will appear at the input of the first NOT gate. So this first NOT gate will invert that input and it will be given to the second NOT gate. And if we see the output of the second NOT gate, then that will be equal to 1. And the same 1 will also appear over here. Now if the switch is instantly connected to the second side, then the same 1 will also appear at the input of the first NOT gate. And this 1 will propagate through the two NOT gates. Or in other words, this circuit will store the logic 1. So in this way, through the feedback from output to input side, this simple circuit can be used to store the one bit of information. But if we want to change the stored information, then we need such two-way switch. Practically, no such switch switches instantaneously from one side to the other side. But what we can do, instead of using the switch, we can use the two input logic gates, where the second input of the gate can be used for setting or resetting the stored information. So in this circuit, instead of the NOT gate, these NOR gates are used. And the second inputs of the NOR gates are used for setting or resetting the stored information. So as you can see, the output of the one NOR gate is connected to the input of the second NOR gate. And the output of the second NOR gate is once again connected to the input of the first NOR gate. So in this circuit, when this S input becomes high, then the output of this circuit will also becomes high. And in this way, this circuit stores binary 1. Similarly, when this R becomes high momentarily, then the output of this circuit becomes low. And in this way, this circuit stores binary 0. And whenever both the inputs S and R are 0, then it will retain its previously stored information. So in this way, using this circuit, it is possible to set or reset the stored information. And for setting and resetting the latch, it has two inputs S and R. So this circuit is commonly known as the SR latch or the RS latch. And more commonly, it is drawn like this. And as you can see, it has two cross-coupled NOR gates. So now, let us understand the working of this SR latch. So let us see what is the output of this latch when this S is equal to 1 and the R is equal to 0. So before we go ahead, let us quickly see the truth table of this NOR gate, because this latch is designed using the NOR gates. So for this NOR gate, when any of the two input is 1, then its output is equal to 0. And whenever these both inputs are 0, then and then only its output is equal to 1. So in this case, this S is equal to 1 and R is equal to 0. So as we have seen, when any of the one input of the NOR gate is equal to 1, then its output will be equal to 0. That means here, the output of the first NOR gate will be equal to 0. And the same 0 will also appear over here. Now if you see over here, then the both inputs of the second NOR gate are equal to 0. And therefore, its output will be equal to 1. That means here, when S is equal to 1 and R is equal to 0, then this A is equal to 0 and B is equal to 1. That means after the application of these inputs in the next state, this A will be equal to 0 and the B will be equal to 1. And if you see over here, then the both outputs are complementary. That means when one input is high, then the second input will be equal to low. Or vice versa, when one input is low, then the second will be high. And in fact, whenever we are designing the latch, then its two output has to be complementary. So let's say here this B output is equal to Q and this A output is equal to Q dash. That means whenever this S is equal to 1 and R is equal to 0, then this Q is equal to 1 and this Q bar is equal to 0. Similarly, let us see the output of this latch when this S is equal to 0 and R is equal to 1. So once again, as per the truth table of this NOR gate, when any of the input of this NOR gate is equal to 1, then its output will be equal to 0. So in this case, since R is equal to 1, so the output of the second NOR gate will be equal to 0. And the same 0 will also appear over here. That means now, both the inputs of this first NOR gate are equal to 0. And therefore, as per the truth table, the output of this first NOR gate will be equal to 1. That means in this case, when S is 0 and R is 1, then this Q is equal to 0 and this Q bar is equal to 1. Similarly, let us see how this latch retains its present state when both the inputs are 0. So let's say currently this Q is equal to 0 and this Q bar is equal to 1. That means currently this Q is 0 and this Q bar is equal to 1. So here the 0 will also appear at the input of this first NOR gate, while this 1 will also appear at the input of this second NOR gate. So as you can see, the 1 of the input of the second NOR gate is equal to 1. And as you know, when any one of the input of the NOR gate is equal to 1, then its output will be equal to 0. That means in this case, the output of the second NOR gate will remain 0. And the same will also appear at the input of the first NOR gate. So for the first NOR gate, since the both inputs are 0, so its output will be equal to 1. So as you can see, when both inputs S and R are 0, then there is a no change in the output state. That means presently, if Q is 0, then in the next state also, this Q will remain 0. And to confirm it further, let us also take the second case, where this Q is 1 and the Q bar is equal to 0. So in this case, when both inputs S and R are 0, then presently this output Q is 1 and this Q bar is equal to 0. So this value of Q will also appear at the input of this first NOR gate. That means now the one of the input of this first NOR gate is equal to 1 and therefore its output will be equal to 0, and the same 0 will also appear at the input of this second NOR gate. So now both the inputs of the second NOR gate are 0 and therefore its output will be equal to 1. That means this Q will remain 1 while the Q bar will remain 0. And as you can see, there is no change in the output state. So far we have seen the three input conditions for the input S and R. So now let us also see the last input condition when the both inputs are 1. So let us see what is the output of this SR latch when both the inputs S and R are 1. So as we have seen, when any of the input of the NOR gate is equal to 1, then its output will be equal to 0. So in this case, since both S and R is equal to 1, so the output of the two NOR gates will be equal to 0. That means both the inputs Q and Q bar will be equal to 0. But actually, since Q and Q bar are complementary, so their value has to be different. But for this input combination, it is getting violated. And in this case, both the outputs are 0. So this input condition is forbidden and should not be used for the SR latch. Moreover, after this condition, when both S and R become 0, then it is difficult to predict the output state of the latch. So in this condition, the output Q could be either 0 or 1, and that depends on the propagation delay of these logic gates. So for this SR latch, this input condition where both S and R inputs are 1 is actually forbidden, and it should be avoided during the operation of the latch. So this is the symbol of this SR latch. So as you can see, it has two inputs S and R, and there are two complementary outputs, that is Q and Q bar. Now so far, this SR latch was designed using the NOR gates. Similarly, it can also be designed with the help of the NAND gates. So now let us see how to design this SR latch using the NAND gates. So if you see this NAND gate based SR latch, then it is very similar to the NOR gate. That means here the two NAND gates are cross coupled. But in this latch, both the inputs S and R are active low. And this is the truth table of this NAND gate based SR latch. So as you can see, in this case, when both the inputs are 1, then there is no change in the output state. That means the next state will be the same as the present state. Likewise, when this S is 0 and R is 1, then this output Q will be high. And likewise, when this S is 1 and R is 0, then the latch will get reset. And in this condition, this Q will also become 0. And this input condition, when both S and R inputs are 0, is forbidden. Because with these inputs, both the outputs Q and Q bar will become high. And therefore, this input condition should be avoided. So now, let us see the working of this latch for the different input combinations. And first, let us see how this latch behaves when S is 0 and R is 1. So if you know the truth table of the NAND gate, then when any of the input of the NAND gate is 0, then its output is equal to 1. And whenever both the inputs are 1, then and then only, the output of the NAND gate will be equal to 0. So in this case, since S is equal to 0, so the output of the first NAND gate will be equal to 1. That means this Q is equal to 1. And the same will also appear at the input of this second NAND gate. That means now, both the inputs of the second NAND gate are 1, and therefore its output will be equal to 0. That means whenever this S is equal to 0 and R is equal to 1, then this Q is 1 and Q bar is equal to 0. Likewise, let us see the output when this S is 1 and R is equal to 0. So when this R is equal to 0, then this output of the second NAND gate will be equal to 1, and the same 1 will also appear over here. Now since the S is 1, so both the inputs of this first NAND gate will become 1, and therefore its output will be equal to 0. That means whenever this S is 1 and R is 0, then this Q is 0 and Q bar is equal to 1. Or in other words, this latch will get reset. Similarly, let us see the behavior of the latch when both the inputs S and R is equal to 1. So when both the inputs of the latch are 1, then it will retain its present state, and there will not be any change in the output of the latch. So let's say currently this Q output is 0 and Q bar is equal to 1. That means this 0 will also appear at the input of this second NAND gate, and likewise this 1 will also appear at the input of this first NAND gate. Now since the Q is 0, so the output of the second NAND gate will become 1, because we have seen that when any one of the input of the NAND gate is equal to 0, then its output is equal to 1. That means in the next state, this Q bar will become 1, and the same 1 will also appear at the input of the first NAND gate. So now both the inputs of the first NAND gate are 0 and therefore its output will be equal to 0. That means this Q will remain 0. So in this way, when both inputs are 1, then the latch will retain its present state. That means if Q is 0 and Q bar is 1, then in the next state also this Q will remain 0 and the Q bar will remain 1. So now let us see the behavior of the latch when both inputs are 0. So in that case, both the outputs will be 1 because we know that when any one of the input of the NAND gate is equal to 0, then its output will be equal to 1. That means in this case, both Q and Q bar will be 1. But as we have seen, both Q and Q bar needs to be complementary. But with this input combination, it will never occur. Moreover, suddenly from this input condition, when the inputs are changed to 1 1, then we cannot predict the output of this SR latch. And therefore, this input combination is forbidden. So this is the SR latch using the NAND gates. And as we have seen, it has active low inputs. Now so far we have seen that how to design the SR latch using the NOR gate and the NAND gates. Now this latch which we have discussed is actually a transparent latch, meaning that as soon as the input level changes, then the latch will respond to that change immediately. For example, suddenly if S changes from 0 to 1, then this latch will respond to that change immediately. But there is another type of latch which has control input, and the control input decides when this latch will respond to that input. So such latches are known as the gated latch. So this is the symbol of the gated SR latch. So as you can see, apart from the normal inputs S and R, it also has the enable input. And this enable input decides when this latch will respond to that inputs. So just by adding the two AND gates, the normal SR latch can be converted into the gated SR latch. So as you can see over here, both S and R inputs to the latch are applied through the AND gate. So in this condition, if the enable input is low, then both the inputs of the latch will remain 0. And in that condition, the latch will retain its present state. Now when this enable input is high, then only these S and R inputs will reach to the latch, and accordingly the latch will respond to that inputs. So if you see the internal circuit of this gated SR latch, then it will look like this. So as you can see, the two additional AND gates are added to the normal SR latch. So here this R dash and the S dash are the inputs of the normal SR latch, and this S and R are the external inputs which we want to apply to the latch. So this is the truth table of this gated SR latch. So as you can see, when this enable input is low, then irrespective of the value of this S and R, this R dash and the S dash will remain 0, and therefore there is no change in the output state of the latch. That means in that condition, the next state will be same as the present state. Now when this enable input becomes high, then these inputs R dash and S dash will be same as the R and S inputs. And in this condition, the gated latch will respond to the inputs. And based on the inputs, the output of the latch will change. So once again over here, when this enable input is high, then this input combination when both S and R inputs are high is forbidden, because in that case both Q and Q bar output will be same. That means this input combination should be avoided. Alright, so this is the design of the gated SR latch. So similarly, now let us see how to design this gated SR latch with the help of the NAND gates. So just by adding the two more NAND gates, this NAND gate based SR latch can be converted into the gated SR latch. But now this gated latch will be active high. So if you see this NAND gate based normal SR latch, then it was the active low. But once we add the two more NAND gates, then it will become active high. So here these S and R are the inputs to this gated SR latch, and this S dash and the R dash are the inputs of this transparent latch. So when this enable input is 0, then irrespective of the value of S and R, the output of these two NAND gates will remain 1. Because as you know for the NAND gate, when any one of the input is 0, then its output is equal to 1. That means whenever this enable input is 0, then this S dash and R dash both are 1. And as we have seen earlier, when both the inputs of the NAND gate based SR latch are high, then there will not be any change in the output state. Or in other words, the latch will retain its present state. That means in this condition, this Q and Q bar will not change. That means whenever this enable input is low, then irrespective of the value of S and R, the outputs Q and Q bar will not change. Now when this enable input is high, then this latch will behave like the normal SR latch. For example, when this enable input is high and when both S and R inputs are 0, then the latch will retain its current state. Because if you see over here, when both S and R inputs are 0, then the output of these two NAND gates will be 1. That means both S dash and R dash will be equal to 1. And since both S dash and R dash are 1, so it will retain its current state. Because as we have seen earlier, this NAND gate based SR latch is the active low. That means whenever both S dash and R dash are 1, then it will retain its present state. That means when enable input is high and when both inputs are 0, then there will not be any change in the output state of the latch. Similarly, let us see how this gated latch behaves when this S is 0 and R is 1. So when this S is 0, then the output of this NAND gate will become 1. And since both the inputs of this second NAND gate is 1, so its output will be equal to 0. That means in this condition, this S dash is 1 and R dash is 0. And since the R dash is 0, so this Q bar will become 1 and this Q will become 0. That means whenever this enable input is high and when this S is 0 and R is 1, then the latch will get reset. Likewise, when this S is 1 and this R is 0, then the output of this lower NAND gate will become 1 because the one of the input of this lower NAND gate is equal to 0. And if you see this upper NAND gate, then both the inputs of this upper NAND gate are 1. That's why its output will be equal to 0. So for this input combination, this S dash is equal to 0 while the R dash is equal to 1. And since this latch is the active low SR latch, so for this S dash is equal to 0, the Q output will become 1 and this Q dash will remain 0. That means whenever this S is 1 and R is 0, then the latch will get set and the Q output will become high. And lastly, when both inputs S and R are 1, then both the outputs Q and Q bar will be same. Because in this condition, both the inputs of these first two NAND gates are 1 and therefore their output will be equal to 0. That means in this condition, both S dash and R dash are 0 and therefore these two outputs Q and Q bar will become 1. So in this condition, as you can see, both the outputs Q and Q bar are same. And just after this input, when this enable input goes low, then we do not know what is the output state of this latch. And that is why this input condition is forbidden. And we need to make sure that these inputs do not appear at the SR latch. So that is the gated SR latch using the NAND gates. Now as I said in the previous video, this latch itself is the asynchronous memory element. That means it responds to the input level change immediately. But this gated latch can be used as the synchronous memory element. So as you can see, if we apply the periodic clock signal to the enable input of this gated SR latch, then it can be used as the synchronous memory element. So in this case, it will become transparent when the clock level is high, and it will retain its present state when this clock level is low. So basically, it will be sensitive to the clock level, or in other words, it will be the level sensitive. So let us understand it with the help of the timing diagram. So let's say these are the S and R inputs to the gated SR latch, and this periodic clock signal is applied as the enable input. So in this condition, now let us see the output of this gated SR latch. So when this enable input becomes high, or when this clock becomes high, then the latch will become transparent to the inputs. So during the on time of this clock, initially this S is 1 and R is 0. That means in this condition, this Q will become high. Now at this point during the on time, the S input becomes low. So now during this remaining time, both inputs S and R are low. So in this condition, the latch will retain its current state and it will remain high during the remaining time. Now after that, this enable signal will become low. That means now during this off time, the latch will retain its present state. So during this off time, the latch will remain high. And once again, it will become transparent to the inputs when this clock signal becomes high. So now during this on time, initially, this S is 0 and R is 1. So at this point, the latch will get reset. And because of that, the Q output will become low. Now during the on time of the clock, at this point, the R is becoming low. So now during the remaining on time, both S and R inputs are low and therefore the latch will retain its present state. That means during this time, the latch will remain 0. Now once again if you see, then this S input becomes high and this R input is still low. That means during this remaining on time, this S is 1 and R is 0 and therefore this Q output will become high. So up to this point, this Q output will remain high. Now after that, this clock signal will become off and therefore even if the input signal changes, then also this latch will not respond to that input level change and in this condition, it will retain its present state. That means during the off time, the output Q will remain high and once again it will respond to the input during the next clock cycle. So once again, when this clock signal is high, then as you can see, this R input is high and this S input is 0 and therefore at this moment the latch will get reset and the output Q will become low. So during the on time up to this point, this R remains high. So definitely up to this point, this output Q will remain 0. But after this point, since R is also becoming low, so both inputs S and R will become low. That means during the remaining on time, this latch will retain its present state and therefore during this remaining time, it will remain low. So if you see the overall output of this gated SR latch, then it will look like this. So in this way, by applying the periodic clock signal to this gated latch, it can be used as the synchronous memory element. But still, it is not preferred in the sequential circuits. Well, why is it so? We will understand it in the next video. And in the next video, we will learn that why the flip-flop is more suitable for the synchronous circuits. And we will also see the circuit of this SR flip-flop. But I hope in this video, you understood about this SR latch and the gated SR latch and how it can be designed with the help of the NOR gate and the NAND gates. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.